I'm Priya Agarwal, and I'm a machine learning engineer at Snorkel, and I'm really excited to welcome you to the Techniques track. If you're just joining us, this event is organized into 3 tracks filled with some incredible talks: the data track, the techniques track, and the applications track. And you are currently in the techniques track. To join sessions in other tracks, you can navigate to Agenda above the stage and select the track that you wish to join and enter the session. Or you could also see Agenda in a grid view. You can go to Chats on the right-hand side of your screen and go to Docs, or visit the Snorkel virtual booth. With that, I'm really excited about the next speaker in this track. The speaker is head of knowledge graph platform at Apple, and he's here to talk about HoloClean and Camino, structured learning for data cleaning and private data generation. Please join me in giving a warm welcome to Ihab Ilyas.
Hi, good morning.
Incredible to have you on stage. Take it away.
Thank you so much. Let me share my screen. So thanks for having me. Today I'm going to tell you a little bit about the journey of a couple of projects that I did while at Waterloo, where I still serve as a professor of computer science. And these 2 projects are intimately related to data-centric AI, but more on the data side. And we investigate how we can automate a very notorious problem of data cleaning and data prep, who has been really a big impediment to AI. As you can see from the logo, this work has been done with my collaborators and students at Waterloo, and HoloClean has been commercialized as a company that was acquired by Apple, where I am currently heading the knowledge platform team. Although today I'm not going to talk about anything that I do at Apple, rather I'm going to give you that journey about HoloClean and a follow-up project called Camino to add a privacy twist to it. So basically, recognizing that data prep is a big impediment for AI, and to be honest, the systems and the advancement that we have in preparing the data is not really comparable to the advancement we have in automating model building. And prior to data-centric AI, when everybody was like rushing on how easy it is to or tooling for generating new models, and to the extent that high school students have been building models to do all sorts of cool stuff for their projects and science fairs, but data prep and data preparation has been left behind. And it continues to be extremely labor intensive, rule-based systems, a combination of tricks, and continues to be costly. And I think it's one of the main drivers for data-centric AI becoming center of attention again, because data was really the most expensive asset in that story. So, give you a context in a toy example that I use all the time about a table that looks benign, like the one you see here, but it's not really good in any way or useful in any way, just because of the amount of errors that is all over it, from duplicates of records of representing the same entity, to value and syntactic error that will prevent you, from example, of understanding how many things happening in New York because one of the New Yorks is misspelled, missing values, and a little bit more subtle kind of violations and errors that requires a context. For example, in this case, we have 2 people with the same zip code but different city, and we know that zip code determines the city in some shape. And usually, data prep refers to this collection of activities that will take this data and kind of clean it up, prepare it to be able to be pushed to downstream models, and then we get insights from this data, and we can do predictions and so on. In the case of structured data, things a little bit becomes messy very quickly, just because of the sparseness of this data. Oftentimes, and I deal with in the startups that I'm involved with, and commercial world, you'll find tables that are hundreds of attributes, but few hundred thousand of records, or even million records, or a few millions of records at a time. And these are very siloed tables, and each one of those correspond to extremely sparse space, not enough redundancy, and errors becomes extremely expensive. Just to take an example of like even how people have been doing record linkage or like even getting duplicates out of this data. And you'll see kind of, all the techniques that will try to generate, for example, similarity metrics between all pairs and trying to kind of run clustering algorithm, all of that, and finally try to merge and kind of predict the canonical representation of every entity. And hopefully that output is a good, clean, duplicate-free data, so I don't, for example, over-represent entities and so on. Depending on the application, some of this over-representation or feeding duplicates in can be extremely harmful. Here, the machine learning task is as limited as comparing two records and probability of P1, P2 match. And for that, we've been using classical ML and decision trees and or even neural models for similarity assessment between kind of the representation of these entities. But it's kind of very well understood problem from kind of prediction perspective. But oftentimes it's the scale that makes it hard. So this is a screenshot of a startup that I founded in 2012, I co-founded in 2012 with Andy Palmer, Mike Stonebreaker, and my student, Mike Stonebreaker and his students and my students. And it's called Tamer, and it does data integration at scale. And this is just 10% of the backend architecture just to get duplicates work. And you can see there's like active learning cycles, and the main thing is how to get rid of the n-square explosion of the space. And for that, people use all sorts of techniques. So it's an engineering and kind of a data prep centric problem that requires machine learning assists, but it's really not. The problem there is, it's kind of not how difficult the model is. It's really how to get these pipelines to work. But if we switch to a different data prep problem, and in this case, I don't want to do duplicates. There is no really combinatorial explosion in the size of the input. It's just the data. And I would like to figure out the errors that are all over the place, the missing values, the syntactic errors, the things that are misrepresented and out of domain kind of values, things that are represented as ranges. And I don't know what to do with this. Like we oftentimes getting this garbage in will throw most of the models off. And the data, as I said, is sparse and limited, and not enough even to learn what these kind of weird representations are for the model to memorize. So for that, we started to see what is the opportunity of building machine learning models to prepare the data for machine learning models. And that completes the cycle. So kind of ML comes as this melting pot of all the signals that we need to be able to build a model that automatically detects anomalies, violations, and hopefully automatically prepare them to the best effort possible without introducing biases that kind of throw the models off, and at least kind of parameterize what humans can look at to prepare this data so they don't spend time on fixing easy errors to fix or easy imputations. That was the goal, and that will avoid the rule-based systems and all of the kind of ugly stuff that we don't like in data prep stacks. But the challenges that we had to solve has to do with how to communicate background knowledge, which is kind of all the bread and butter of most of these systems. And if you hear all of these snorkel talks and the panels that I saw this morning, and you can see how domain knowledge about how to get a specific entry or interpreting a certain value, or even talk about what a violation is extremely important. And it's not clear how to communicate these violations and rules to a machine learning model. And we definitely don't want to have a hybrid system or both systems where you have a statistical model try to do cleaning, and you have still your rule-based system that trying to kind of do things in a kind of a symbolic way, and we have no clue how to combine these things. That's the first challenge. The second challenge is, of course, lack of training data. And since this is a weak supervision is a very widely used here. So how do we generate enough data to train a model of finding errors? And it turns out it's a little bit more difficult in our case, and there's no really availability that much for labeling functions like snorkel style, for example. Although when it's available, we should definitely use it. But oftentimes, we don't know even what are the rules that constitute an error. We just know the data, and we would like to know what are the things that doesn't make any sense, and what is the best value that replace it. So it doesn't lend itself directly to kind of labeling functions, and how to make this at scale. So, I dumped at you a bunch of challenges that was the reason, and that kind of give the birth to HoloClean collaboration between like myself in Waterloo and my students, and Chris Ray in Stanford, and Theory Katsinas, who was postdoc at the time in Stanford and later became a professor in Wisconsin. And then that led to a line of work that we're trying to understand how data get polluted, and can we represent data cleaning problem as prediction on a probabilistic database model. And just to give you a glimpse of what does that mean, one way to think about errors, that they're not really random, but they are generated by a pollution model or a realization model that messes with the intention model that generated the clean data. So data was born clean. There is a model that injected errors in a certain way. And what I'm observing, this J star, is a polluted instance. And data cleaning or missing value imputation or data prep in general is getting the most probable I that generated this J star that I'm observing. So simple enough. And if we can kind of parameterize some of these models and learn from the data estimates of these parameters, we probably can use these models to predict for every cell in my table or for every property in my knowledge graph, what is the most likely value here, and is it different from what I'm seeing or not? That is a nutshell. And without going through, like, these are just symbolic way of saying that there is a way to also inject into these models things like violations of rules and constraints and business logic that I already know about. So now we've been able to also communicate domain knowledge to these models by saying, for example, instances of the data that do not violate this particular business rule is more likely to happen than instances of the data that have huge violations to this business rule. These business rules can be things like, instance that's coming from New York, employees that coming from New York should be paid more than people working outside New York for the same role just because of the taxes or something like that. It can be as complicated as you want, as long as you can communicate the violations to this model. Practically speaking, it's kind of a contextual representation of the data for every cell in our structured data, and an attention layer that's trying to kind of attend to the important properties and columns around me that has high effect in predicting my value. So if I'm investigating, for example, the birth date of a certain person, or the salary of a certain employee, or the SKU of a certain product, I would like to have a contextual representation of that value, given all the values that appear with me, paying attention more to the columns and the properties that are highly correlated with me. And that schema level attention was kind of an interesting idea, because now I'm kind of lifting that learning to something that has enough redundancy in which I can learn something. So even if the data is very sparse, I probably can learn a lot of nice information about how the certain properties and columns in the data affect each other. And under the hood, there is this self-supervision in which I can try to build that model or train that model by masking every value I know and try to predict it back. And one of the questions you might ask is, like, if you're trying to do this, I thought you're trying to get errors. What can you actually learn from data that has error, a useful model that can clean this data? And it turns out, with some math behind it, that if there is enough good, more good than bad, then you can probably learn very useful model just because of how rare these errors are, and there is enough good data to train the parameters of these models that I just mentioned, and then you can use these models back to predict what's wrong. So just for example, some of the side effects, we know this. We can now have heat map of what's important and what kind of columns important, what other columns, and we use that to predict. For example, in this case, I want to predict the county of that record. So I know that Chicago is a city. I don't know the county. And I know this is the zip code. I know the age is 35 of that person. And if I can kind of have an embedding or a representation of all of these values that appear in that record, then I can use those in a way by attending more to the columns that kind of predict me better. So in this case, for example, if you look at the county error, city is probably not a very good predictor of what county it is, but zip code is a very strong predictor, and age is very unrelated. So I'll probably pay attention to the importance of the zip code, and then among all possible candidates of county, I can come up with a PDF or a probability distribution of what is the most probable county that belongs to this context. And the red part that you see there is our ability to inject in these models things like violations of business rules and other sparse features. So the details really here are not that important, and there is like a lot of paper that you talk about this. I just want to communicate to you that there is a lot of techniques that we know from transformer models and contextual representation and embedding that can help with a classical problem like data cleaning if you can find the right representation and mix these sparse features in the representation of every cell. Then you have a very strong predictor that will learn how data was generated and use that model to be able to do very useful missing value imputation tasks, error detection tasks, or even predictions. In fact, in one of the use cases, we been able to repredict manual labels of huge data sets with extremely high accuracy just by learning a model that describe how, for example, to predict the SKU for every product in this market research use case. In fact, we beat the human because we thought we have accuracy 96% or 97%, and we looked at the 3% difference between us and the ground truth, and most of this was already errors in the ground truth sometime because labels were not perfect. It's not as awesome like this every time because there are challenging data sets when there is not enough redundancy or a lot of independent columns, and in this case you're shooting in the dark a little bit, but in general you can get very good results. So hopefully I can just convince you at least to kind of look at HoloClean, and there's a lot of material on the open source version of HoloClean, holoclean.io, and it has blogs and some research papers and the idea of probabilistic data modeling and data cleaning, and it's even available on GitHub to play with if you like. And that data preparation is possible to be on the automation path at least. So data comes in, I can run it through these models that do not really do any prediction task, but try to predict the sanity of the data itself before I can feed it into kind of more task-oriented models that will try, for example, to do aggregates or to do predictions or generate insights. So think about it as kind of ML for data sanity before we get it into normal ML. There is a lot of debate like, do I need this layer? Why, if I cannot make, for example, my downstream models even bigger, why cannot do this task implicitly? And I don't have time to debate this with you, although it's an extremely interesting topic. I still believe that the task of HoloClean is extremely limited and targeted for this data cleaning, and for a lot of sparse data sets, it's still useful to think about those as a kind of a separate step. So cleaning by modeling how data was generated and how errors were introduced to recover the original data value is extremely powerful idea. And one of the side effects that you learn is a model that is describe how data was generated. So, and we start thinking like, if this is true, then why can't I use this model not to really clean a data set, but to start sharing this data set and generate samples that came from the same distribution. So we looked at how people kind of worry about privacy and so on. So I have a model, or I have there's a firewall, all my data is there, and I would like to share it across organization. And in any big organization, you will know that legal department is extremely powerful, and even across business units in the same org, sharing data is in a need-to-know basis, and there's a lot of clearances and disclosures, and oftentimes you would like a sample that is anonymized and private. So the question is, can I generate a synthesized data set from my original data set, and I share it with another department or another organization to get insights and run general purpose learning? So we thought, what do people do? For example, in differential privacy space, and just a quick reminder, differential privacy is just a randomized randomized mechanism that allow you to obscure the data in a way such that you can prove that you cannot tell the difference between two neighboring data sets that different in one in terms of the output. In a nutshell, basically you cannot tell with very strong probability, you cannot tell if a certain instance is inside data set. And oftentimes this is good enough to stand in the court of law to say that this data is private, because you cannot with high confidence know individual information from what I give you. So that's a powerful idea, and there is a lot of literature in generating a synthesized data set from original data set that is differentially private, i.e. you cannot learn from it anything about the individuals of the original data set. This is great and dandy. The problem is, in doing so, oftentimes we destroy all the correlations and the structure in this data. We actually butcher it completely, and that makes it, while useful for maybe some aggregates and some tasks, not useful for consumption in a machine learning model that, for example, learn something from these correlations or understand how column A depends on column B, or how important this property for this other property. So the utility is quite low, and you really cannot recover these back. So we thought, like, can we synthesize the data and then we try to clean it? And that's not true, because most of the data has been, like, the structure of the data has been compromised. So the question is, can we come up with a system that sits behind the firewall, that learn how the data is generated, but still in a private way, such that when I use that model to generate a sample, this sample is randomized enough, but came from the same distribution? And that gave birth to Camino, who's led by my PhD student, Chang, who just graduated and now starting his professorship career. But the main question was, can I privately learn cleaning models to generate private structure? And the opportunity, as I said, is we have a model that will learn that underlying probabilistic model for free. So question one, can we learn that model privately? And question two, this model was designed to predict data, a cell in a data set is not invented. It was not designed to generate synthesized data from an input data set. So Camino solved these two problems. I'm going to give you just a teaser, but you should look at the VLDB paper from 21, and it's also open source. And basically, we would like to generate a data set that looks very close to the original data set. It enjoys the same structure, it enjoys the same business rules, but it's differentially private from the original data set. Two main topics that kind of contributed to this success, building on the privacy and security community, and the idea of being able to train a model in a differential private way by carefully injecting random in every step of the learning, for example. And so learning the model itself can be done privately. What was remaining is, can we use that model in a way that is useful to generate the data as a data synthesizer as opposed to data cleaner? And if you remember, this is the model that I showed you earlier, for example. It's like a exponential family that tell you, for example, that the probability of a data instance that does not have violations, this V is the number of violations in the data set, and W is like a weight. And it's designed such that it takes the whole data set and see what is the probability of this data set. So with some kind of clever decomposition, we can actually decompose it such that it can do this prediction at a cell-by-cell basis, such that for every cell, I see what is constructed so far, and I predict what is the next possible legal value for the cell that I'm trying to synthesize. And Chang created that iterative process that basically do kind of a raster scan on your data set. So I start by an empty table after I learn the model, and I start populating these cells by picking value from the distribution. And what you end up by private data set that came from the same distribution that has high utility and can be used for drug research or other things, even if it was generated from very private data set about patients, for example. So I hope that those kind of shed some light about what we have been doing in using ML and AI for data prep, such that it's sane enough to be used by, and gonna end up by giving credit to my collaborators in the Holoclean team: Chris, Theo, Nina, Alireza, Josh. Josh, by the way, is in Snorkel now. Omar and Ryan and Nina are in Apple, because, and Theo and I are in Apple as well. And the Camino team is my good collaborator, she's assistant professor in Waterloo, and she's a privacy expert. And the main lead was, and her student, and the main lead was Chang, who graduated this year, and he did most of the work. So extremely honored to work with this talented set of collaborators. I learned a lot from them, and we did some cool work. So with that, I hope you enjoyed this, and I leave you with automating data cleaning infrastructure is a cool idea. It has a lot of ML challenges. It uses self and weak supervision. It celebrates contextual data representation and embedding, and it has direct application, error anomaly detection, data repair, but also private data synthesis. I hope that's useful. Thank you.
Yes, that was such a fascinating talk, Ehab. It was incredible learning about how the data in wild is so unclean and your probabilistic approaches to cleaning it. We do have a few questions from audience in the chat. Would you mind just going full screen and stop sharing your screen so that the audience can look at you for questions?
Sure.
Perfect. The first one is from Carl, and they ask, are there limitations of this technology to structured data sets, or can unstructured data be used as well?
I mean, in the underlying idea is definitely applicable across the board, but this particular technique celebrates the structure. It actually leveraged the structure to try to create a dent in the sparsity problem by saying, if I learn at the structure level, not at the instance level, then I can, by this kind of lifted learning, I can learn a lot, because I can accumulate a lot of mentions and observations to the same structure. In a completely unstructured, you have, there is a plenty of technique that depends on a lot of redundancy and a lot of repeatedness, which might not be available in structured data. So
that makes a lot of sense. Yeah, I was wondering the same thing, because noise usually doesn't have patterns. So you would need a lot of data with some repetitive patterns that take place in noise to be able to clean it. That makes sense.
That's right. That's right.
Perfect. We just have maybe like 30 seconds for this next question. It's by Hussein, and they ask, how is similarity measured? Are these techniques valid for graph data type using privacy in a synthetic data setting?
Okay, so in 30 seconds, so definitely everything I talked about today works on graph databases, or like the fact that I'm using tables is just anecdotal and just to show that there is structure. But structure should be taken in its broader sense. So any structure in which you have kind of a schemish kind of way of describing the structure in your data, it's applicable. Similarities and other things are, often plugged as extra models, either learned view neural models or injected as kind of business rule similarities. And have a look a little bit at these techniques, and you should be able to see it's directly applicable to any type of kind of structure in the broader sense of structured data.
Perfect. That was amazing. Thank you so much for your time.
Thank you. Thanks for having me. Take care.
Of course. Up next, on the main stage, please join us for Mindful Reset with Kartla. It's a short talk about dealing with a chaotic mind, followed by an 8-minute mindful meditation. And I will see you there.